Hi, everyone. A couple of you came by this afternoon to talk about this incline problem. So I thought I'd try to put together a quick video just going over how to set up the solutions to question number 5 and number 6 on the homework. And number 5, you're trying to find the force acting on this block as it slides down the incline. There is no friction on the incline. We're given the mass, the height of the incline, as well as the angle. Number 6 is the one that involves a little bit more work. That's to find the time it takes to slide down the incline. So let me just get started. Now, I'm using my iPad as a graphing tablet. It's not quite as fancy as one I'm usually working with, so bear with me if my writing is not as crisp as it could be. But so what we have is the first thing we're going to need to do, of course, is to label the forces. Let me get my things back in line. A little jumpy. All right, so I'm going to label the forces. So I'm going to use blue for that. So the forces acting on the block, I have the weight vector going straight down. And I'm going to label that mg. That's the force of gravity. And I have the normal force, which is perpendicular to the incline. And that's it. Those are the only two forces. Now, to solve the incline problem, my acceleration is actually going to be down the incline in this direction. So if I use a traditional XY axis, then my acceleration is going to be in both the X and the Y, both the vertical and horizontal, and that's going to be a lot more work. So instead, we tilt our heads and decide to set our axis this way. By doing it this way, then my normal force is now in the y direction. My acceleration is now in the x direction, but my weight vector is now not in either just x or y, which means that I need to break the weight vector up into components. So I'm going to do that. So my weight vector is going to go down about this much in the x-axis. So I'm going to label that mgx. That is the x part of the weight, or I could also think of it as the mass times the x part of the gravitational acceleration going down the incline. And then there's going to be the y piece. And label that mgy. And that's going into the incline. So notice that the two components always make a right angle with each other. So that's always a right angle. So for this question, I don't really need the y component of the weight, but from the force diagram, the y component is actually over here, by the way. I just drew it there so it's tip to tail and it completes my triangle, my vector triangle for the weight. But notice that really that mgy is going to be equal and opposite the normal force in this problem. Those are the only two forces perpendicular to the incline. But the force that's making me go down the incline is mgx. So that's the one I have to find. In order to find that, though, I need to know this angle on the inside of the vector triangle. Now, you can do a little geometry. If you remember, so this is also a right angle. The three angles of a triangle must add up to 180. So whatever angle A is for you, this angle over here, this angle right here, let me just do it that with a tick mark there. This angle is going to be 90 minus A. But if that's 90 minus A, then this angle must be A. And that's always going to work out that way for these incline problems. So, but normally I would associate the x component with a cosine function, but now I see my x is opposite the original angle of the incline. That's actually going to be sine. So now I can set up and find out what mgx is. So I know that sine of my angle, and remember the angle is known in this problem, is going to be equal to the opposite side of the triangle, which is that x part of the weight that I'm looking for, divided by the actual weight, mg, because the vector is always the hypotenuse. So now I can just rearrange that, and I'll get that mgx is going to be equal to mg sine of angle A. I know that. I know G. I know M. So that's it. That's the answer to problem 5. I just plug in the mass gravitational acceleration of 9.81 and the angle into the trig function. And I have the force down the incline. So number 6 is a little bit trickier. Because number 6, they tell me the h. So in this problem, I know h and I know the angle A. But they don't tell me this distance down the incline. That's my actual delta x. So that distance down the incline is actually the hypotenuse of this incline. So I can set up trig functions to actually find out what that delta x is. So for number 6, I have a couple of steps to do. I note that sine of that angle A must be equal to the height divided by my hypotenuse, which is delta x. That means that delta x times sine of the angle is going to be equal to height. But I want delta x, so that means that delta x is going to be equal to the height divided by sine of the angle. Now, if you remember, the hypotenuse of a triangle is always the longest side. So if you solve for delta x and you get a number smaller than the height, you know you made a math mistake somewhere. So I have delta x now. So now to get the time, I'm going to need to do a motion equation. So I like this equation for this problem. Because VI equals 0, I can cross that piece out. And then I note that the acceleration, I know the force down the incline, so I can actually solve for the acceleration as well. So the acceleration is simply going to be equal to mg sine theta, sine of angle A, because that's the force going down the incline, divided by the mass. So A is actually just going to be equal to G times the sine of the angle. I didn't even need the mass to find this. Then I can just plug in and solve for delta t. So, I'm going to multiply the 2 across, and I'll get that delta t squared is going to end up being 2 times delta x divided by that acceleration, and then you just take the square root of both sides, and you're good to go. All right, so that's just a little tip. I know it's a little crowded, but like I said, I'm just doing this on my iPad right now, so I wanted to try to get this posted so people can review it. So number 5 is the easier part of the problem. It's labeling the forces on the box and then breaking the weight vector into a component down the incline and into the incline. Number 6 is involves a little bit more trig and review of a motion equation. All right, hope this helped. See you in class.